Hello everyone, my name is Minmin. In this video, I will talk about our paper, SimpliMix, a simplified manifold mix-up for few-shot point cloud classification. The following sections will be introduced in this video. Few-shot learning often assumes that base classes are abundant and diverse with plentiful well-labeled samples for each class. This assumption ensures that models can generalize effectively from a small amount of data by leveraging prior knowledge learned from base classes. And we find out that the assumption holds for 2D few-shot learning, since the benchmark datasets, such as mini-ImageNet, are large and diverse, but 3D point cloud few-shot benchmarks, such as ModelNet 40, are low in magnitude and diversity. In this figure, we clearly show the magnitude difference between the two types of benchmarks. We argue that networks trained with such low numbers of base classes are more prone to memorize and overfit, and we conduct experiments and show that low number of base classes does affect the generalization. We use DGCN as the feature extractor and ProtoNet for the few-shot classification. We took the first 10 classes, the first 20 classes, and 30 classes for experiments. The results are shown in Table 1. We can see that the greater the number of base classes, the higher testing accuracy. Moreover, we visualize the embeddings of some base samples and novel samples from experiments 1, 2, and 3. The base classes embeddings from experiment 1 cluster more tightly than the embeddings from experiments 2 and 3. However, the novel classes embeddings from experiment 1 are not well clustered, and clusters from experiment 3 are better separated as anticipated. Taking both results in Table 1 and Figure 2 into consideration, we can conclude that models trained with lower number of base classes are more prone to overfit and have worse model generalization. So how can we alleviate the overfitting issue without collecting and labeling new data or generating synthetic data using generative models? We propose a simplified manifold mix-up called SimpliMix, which mixes hidden representation and forces the models to learn more generalized features. Before we dive deeper into the SimpliMix, let's give a brief introduction to mix-up and manifold mix-up. Zhang introduced the concept of mix-up as a data augmentation technique. It randomly sampled two sample examples, xi, yi, and xg, yg from the training data and linearly interpolates them. However, manifold mix-up is an extension of mix-up. Instead of linearly interpolating input data, it interpolates hidden representations of data. Given a deep neural network, they randomly select a layer L to mix up two data with mixed hidden representations of data and their soft labels as training signals. It improves the generalization of the neural networks by smoothing the decision boundary and flattening the data class representations. Inspired by the manifold mix-up, we adopted the idea of linearly interpolating samples in the feature space to enhance model generalization. For 5-way one-shot one-query task, we get 5 support samples and 5 query samples in total. First, we feed the inputs to the feature extractor and process them until reaching layer L and get an intermediate batch. Second, we shuffle representations of samples and get a new batch of representations. Third, we mix 2 batches of samples by randomly selecting a subset of points with the size of lambda times w and another subset of points from the shuffled batch with the size of 1 minus lambda times w. The mixed representation hi hats are constructed by taking the union of the 2 selected subsets. Lastly, we force each mixed query to be close to the
classes of the samples they get mixed from.
This is the loss function. We use the cross-entropy loss twice given that each mixed query data is a combination of two samples with labels yi and yi prime. There are two differences from manifold mix-up. The first is that we sample lambda from the uniform distribution, while manifold mix-up adopts a beta distribution with alpha adjusted for different datasets. Secondly, we compute cross-entropy loss twice for each mixed query samples, while manifold mix-up constructs soft labels as targets so that the network learns a smoother decision boundary. This is the architecture of DGCNN, which acts as a feature extractor in many papers. Here we point out the possible places where SimpliMix might be applied. We conduct within dataset and cross-domain few-shot learning experiments to show the effectiveness of SimpliMix. For within dataset experiments, we construct 3 datasets, which are obtained from ModelNet 40, ModelNet 40C, and ScanObjectNN by resplitting the chain and testing sets. For cross-domain experiments, we choose base classes from synthetic datasets and novel classes from the real-world ScanObjectNN datasets. We take 3 baselines, ProtoNet, CIA, and ViewNet. We incorporate our SimpliMix into them and name them as ProtoNet SimpliMix, CIA SimpliMix, and ViewNet SimpliMix. The results show that SimpliMix consistently improves the performance of all networks. This is the cross-domain results. We train on the source domain and test on the target domain without fine-tuning. All methods achieve higher accuracy when SimpliMix is incorporated, which proves that networks with SimpliMix lead to more generalized representations. Moreover, we visualize some class representations of ScanObjectNN. The embedding for classes shelf, bed, and sofa obtained with CIA SimpliMix are better clustered than CIA, and the clusters for classes display and door from CIA SimpliMix are more compact. In the ablation study, we first compare the mix method used in SimpliMix with other 2 methods. One is QMix, which only mixes the query samples and leaving the support samples unchanged. The other one is called SQMix, which mixes support samples first and then mixing the query samples based on the way supports are mixed. As expected, all mixing methods outperform ProtoNet, and SimpliMix performs best in the 1-shot setting. For the 5-shot setting, SimpliMix and SQMix perform comparably. Overall, SimpliMix is favorable since it is easier to implement. In SimpliMix, we sample lambda from uniform distribution with a range from 0 to 1, which is equivalent to sampling lambda from beta distribution, where when alpha equals to 1. We also experiment with different beta distributions by taking various values of alpha. It shows that sampling lambda from the uniform distribution achieves better average performance than sampling from smaller values of alpha and slightly better results than sampling from larger values of alpha. Therefore, we choose to sample lambda from the uniform distribution for simplicity. In conclusion, in this paper, we demonstrate and draw attention to the effect of size disparity between 2D image and 3D point cloud few-shot datasets, and propose a simplified manifold mix-up called SimpliMix to improve the network's generalization. We conduct experiments, including within dataset and cross-domain few-shot experiments, and improve the performance of many prototype-based methods by incorporating SimpliMix.